Okay, well, welcome everyone to another Gazebo community meeting. Today we're going to have a presentation that is going to take the entire meeting. Nate's going to be talking about the DARPA Subterranean challenge and how Gazebo was used to run the competition on the cloud. Before that, as usual, we're going to go over the agenda real quick for 5 minutes. We're going to then have the presentation with time for questions. And then if people have anything that they'd like to discuss, feel free to add items here at the bottom. We're skipping the news section for this week because Kat is out at ICRA. So without further ado, let's get into the agenda. So for announcements here, another reminder that ROSCON call for proposals is still open until the 9th of June. So you have still a week or so to submit proposals. The diversity scholarship application is also still open until the 13th of June.
Yes, please have people apply for that. Right now, we don't have a ton of applications. I know a ton will come in at the last minute, but the earlier you can do that, the better.
Yeah, thank you, Michael. And then for, in case you missed it, this Monday we had the release of ROS2 Humble. It's the next ROS2 release. It's an LTS, so you should definitely check it out. It runs on Ubuntu Jammy, and it has Gazebo Fortress support out of the box with the ROS Humble Desktop full package. So be sure to check that out and try it if you're on Ubuntu Jammy. Another thing here, we've had just one announcement of releases since the last meeting. This one, we had some new features on, for example, SDF, the conversion between SD format to USD, the Universal Scene Description, which is maintained by Pixar. So now you can use that inside Gazebo Fortress. There's also a visibility mask for LiDARs. This is something that we hadn't done before. Before, cameras had visibility masks, but not LiDAR, so you can get that as well. There's a nice convenient CLI to print the inertial stats of an SDF model, so you can get properties of the entire model like this, like the center of mass and the moment of inertia for all the links combined. And also there's more and more Python interfaces now. We got Capsule, Ellipsoid, and you can use it from Python. Here's a snippet example. The entire changelog is here in the post if you want to take a look. And finally, Open Robotics is hiring. I mentioned this last month. So we have some positions in Singapore, some positions in Mountain View, California. And we are taking remote applications for people elsewhere in the world. So be sure to check these out. Okay, so I think we're ready to get into our main presentation. Today it's going to be Nate Koenig presenting about the DARPA Subterranean challenge and how that was run using Gazebo. So Nate, you're up.
All right, thank you. Let me get this running. Okay. All right. So just one quick caveat for anyone that actually participated in this challenge. I'm going to be using the word Gazebo to talk about simulation when in fact you are probably using Ignition. That is just a reflection of our name changes, and I'm trying to stick with our modern lingo going forward. So this was a challenge run by DARPA, and we participated mostly on the simulation side on the virtual track. And there's quite a few slides I have in here. So if you have a question or want some clarification, it's best to just either raise your hand or shout at me before I get to the end, because it could be a while before I get there. So let's talk about just a general overview of what the DARPA challenge is. There have been a long series of challenges from DARPA starting way back in, I'm not even going to try to remember the years, early 2000s with the Grand Challenge, where they were doing autonomous cars in the desert. the idea with challenges was to bring in people that were not typical performers or participants in a DARPA project, where a typical performer would usually be a research institute, a place of higher learning, or large corporations, and instead open up the playing field to pretty much everybody, and ideally get new and novel approaches to hard and difficult problems and domains. So the SubT challenge moved into, excellent ads, thanks YouTube, into the underground space. So they were looking at exploring subterranean environments and finding artifacts or objects of interest using a team of robots. There were 2 tracks, the systems track and the virtual track. The systems track took place with real robots in real physical environments, and the virtual track took place in, obviously, virtual worlds. Besides the difference between reality and simulation, the other primary difference, well, I guess including prize money, is also that systems tracks competitors were allowed to use teleoperation within the confines of communication range, whereas virtual teams had to be fully autonomous. This challenge started off in 2018, so quite a while ago, and ran up until September of 2021, so just last year. So this just wrapped up last year. And there were 4 primary competitions that took place for both systems and virtual track. Excuse me, I think the only caveat here is that the cave circuit systems track was not held due to the pandemic. It was pure virtual for that particular event. So each circuit was meant to capture a particular domain. So tunnels were human-made tunnels, urban would be subways, warehouses, that type of thing. Caves are pretty much self-explanatory, and the final event was meant to be a mashup or a triathlon type of scenario where all 3 domains were experienced by the teams in one world. So let's make sure audio is working. And this is a little overview by Tim Chung.
Underground settings are becoming increasingly relevant to global security and safety. Rising populations and urbanization drive the demand not only to build up, but also to build down, requiring first responders to perform their duties underground. In many ways, subterranean environments have remained an untapped domain in terms of developing breakthrough technologies for national security. That's where the DARPA Subterranean Challenge comes in. We're looking for audacious ideas on how to overcome the numerous difficulties these locations present. Poor visibility in communications, difficult access, and unpredictable terrain among them. Teams in both tracks will compete in 3 preliminary circuit events and the final event. Each circuit event will explore the difficulties of operating in a specific underground environment. The first will focus on human-made tunnel systems. The second will focus on underground urban environments such as mass transit and municipal infrastructure. The third will focus on naturally occurring cave systems. In 2021, we plan to hold the final event, which will put the teams to the test with courses that incorporate diverse challenges from all 3 environments. The winner of the systems track will take home a $2 million prize, while the winner of the virtual track will earn a $750,000 prize.
All right.
Underground settings are becoming.
All right. So that's a little overview of the scope and feel of the challenge. This slide is here purely so that people have links to get started if you so choose. Everything should actually still run and operate. The first link here for the SubT simulator is our code base that's specific to SubT. So this holds all the worlds, plugins, robots, and whatnot for SubT. The SubT Hello World is a example solution for SubT. This is meant to be a good starting point if you want to develop your own solution. It uses off-the-shelf components to build a ROS-based control stack for a multi-robot solution for SubT. If you're looking for the rules and all the resources associated with the SubT competition itself, that's the third link. And the fourth link on here is our Gazebo web application, which was the primary tool used to host simulation assets and run your solutions on the cloud. Okay, so let's jump into the weeds a little bit. Starting off simple, the general high-level architecture of how we established the SubT virtual environment looks, or should look, very familiar to people. You have your running instance of Gazebo with all the plugins, worlds, and robots that you want to simulate. And then you talk to your ROS-based solution using the Gazebo ROS bridge. So that's a pretty common architecture that we've used in the past and many people use in their robot development environments. However, we needed multiple robots, so not just one, but a whole team of robots. And we accomplished this by Dockerizing each of these solutions and bridges. And the purpose here was to kind of mimic locally what you would get when running in the competition space. So important aspects here are that robots cannot directly talk to each other, so they couldn't have, say, a shared ROS master and communicate via normal ROS topics. You would have to go through a communication model, which I'll talk about shortly. So we made this relatively simple to test locally using Docker Compose, and we have some scripts in the OSRF repo to make it easy to start and stop this type of environment locally. The major problem with running multiple robots and simulation on a single computer is that it can be resource intensive, especially if you're going down the path of using machine learning on one or more of your robots. It will become intractable to get results out of simulation in a meaningful time frame. So that brings us to the cloud. We offered a cloud solution for teams for practice, and this is also the same technology we used for running the competition itself. This was a completely managed environment in which we would launch EC2 instances, deploy the appropriate Docker images to these images, EC2 instances, and start and stop simulation appropriately. All that teams would have to do is supply us with the images that contained their solution and tell us which robots they wanted to use for each Docker image, and we would take care of the rest. So this was a way to have teams practice with many robots and get results back in a reasonable manner. They could run multiple simulations simultaneously, so that they didn't have to wait for one to finish before getting the next. At the end of the day, once a simulation ends, log files will be uploaded S3, and teams will be able to download those logs via the web application. More to come on that in the future slides. So before I go on, I'm going to talk pretty much about each one of these components in a little bit more detail, and then move into the competition itself and how teams competed and how we ran the solutions. So I'm going to start with worlds and how we built the worlds, released the worlds, and how you can potentially use these resources in future programs. So we had the goal of creating worlds that were representative of what you would find in the real world. And this sometimes played at a right angle to the challenging aspect that DARPA was also trying to achieve. So we didn't want super simple worlds. We also didn't want overly complex worlds. So we struck a middle ground through most of these worlds that you'll see through this presentation. So this is just one example. This image is a top-down view of a tunnel environment. It's very rectilinear, a lot of branching. This is meant to capture the style of human tunnels, which tend to be straight, right angles, and whatnot. but also adds a lot of challenge in terms of the overall complexity. The one driving motivation was also to allow us to create multiple unique worlds from a relatively small set of tiles. So this world you see here is made up of relatively small, I think they're roughly 10 meters by 10 meter tiles stitched together to form this world. And then we could, make any number of worlds based on those tiles. So the components to each world consisted of a staging area. You can see my mouse, excellent. There's a staging area down here. The staging area is meant to be the location where all robots are spawned at the start of simulation. Then attached to the staging area are the series of tiles. Within these tiles are artifacts. These are the objects that teams are meant to find, and when they're found and correctly identified, they score points. Later circuits, if you recall, there was a tunnel, urban, cave, and then the final event. At the cave circuit and beyond, there were dynamic obstacles, rock falls, and tunnel collapses, and particle emitters. And there was always a communication model. The communication model is meant to capture inter-robot communication and model what you'd expect to get in subterranean environments. All right, let's go into some of the staging areas. So each domain had its own staging area. They were meant to be consistent across all teams. Each robot was spawned in a grid pattern, so that all teams started in a similar fashion. It also held a location for a team's base station, which is meant to be pretty much a compute node that was immobile, and they could use that to coordinate their team. And it was also a place that held the command post. The command post was essentially a reference frame in which teams had to report artifact locations. And each staging area also had a pretty clear gate. Once a robot passed the gate, that would essentially start the clock. And at that point, teams would have 60 minutes of simulation time to run their solution. Let's see. Oh, I'm not sharing. 1 second. I want to share my window and not a tab. Pardon me. Okay, we're back. Right, so I can quickly give you an idea of what each of these staging areas looks like. And the purpose here is kind of show you the progression of staging areas. We started off, this was the tunnel staging area. It was originally a flat ground plane with a really simple entrance to the tunnel. And then we realized that if you had a quadcopter in the staging area, it was easy to fly it vertically upwards and then see the entire world. And so you could essentially get a map of the environment without actually exploring the environment. So we added these giant walls. So we learned from that experience, the urban environment was a little bit easier because we could just put the robots in a warehouse-like space. So this had a clear ceiling with a gate and whatnot. So we didn't have that aspect of trying to see the entire world prematurely. You'll also notice that these starting areas each get a little bit more complex as we go on. This just kind of reflects the additional time we had and experience gained in terms of creating staging areas. And this was the cave one. These walls were obviously put there to limit visibility to the rest of the world. And the final one was a futuristic urban style environment, which mimicked the staging area used in the final event. Nicely branded, looks kind of almost Star Trek-y. So those were the staging areas. See, I don't want to be full screen. You guys can still see that? Well, I'll go full screen, fine. All right, so each world consisted of tiles. As I mentioned before, each tile is essentially a mesh that had a visual and a collision, and they were created either by hand, using our very skilled 3D artists, or they were generated from point clouds, but that also typically required a lot of manual tweaking and tuning by our 3D artists as well. Big shout out to Cole, who did a lot of this and made our worlds look awesome. So along the way, he also helped create some nice tutorials. They're all on the Gazebo documentation. In case you're interested on how to convert point clouds to meshes, there's a blender to SDF exporter, how to optimize meshes for simulation, and the last one is just about creating SDF that's suitable for simulation. Each tile had connection points. In this image down here, you'll see them highlighted in yellow. Those connection points were put into a lookup table so that we could write a script that would allow us to randomly generate worlds based on the domain type of the tile and the connection points. And then each tile would be uploaded to Fuel so that we could visualize them in the web application, and also easily have a nice consistent place in order to have all the assets in a collection and be able to download them at runtime. So each world that we built went through a validation process. There were some scripts that we wrote to make this a little bit easier on ourselves. One was a connectivity checker, and that basically would fly you through the world to each tile junction point, just to make sure that there's no gaps and tiles were aligned. There's an artifact checker, which did a similar thing, but this time for artifacts. So it would fly you through the world, stopping at each artifact, and you can make sure that they were not floating in space or not penetrating the ground plane or things of that nature. And we could also visualize the communication model. So this bottom image down here shows that visualization where tiles would be highlighted in different colors based on whether there was a connection between a source and destination point. And you could check to make sure that there was no weird behaviors going on in your world in terms of how the communication model worked. And then the final validation step would just be to drive or fly through it. And this would be done by a couple people just to make sure that the world looked okay from the perspective of the robot and didn't have any weird bumps or catch points for the robots. So we went through a few iterations in terms of just generating the worlds themselves. We started off using a spreadsheet approach, which allowed us to lay out the tunnel environments pretty easily. So this approach relied on generating a CSV file by hand, where each cell in the spreadsheet would contain information about what tile you wanted and whether or not it had an artifact, and also some pose information about height in the world and its rotation. So this was easy to set up. It was relatively easy to write a script that would parse the CSV file and generate an SDF file from that. The primary problems were that it was a little bit inflexible, especially with tiles that were not very regular in shape, which became more problematic with cave and urban tiles. And also was a little bit more difficult to add elevation, significant elevation, because a spreadsheet essentially is flat. And so trying to add multiple layers would require multiple spreadsheets, which became difficult to manage. That led us to the random world generator. So this is tying back into the connection points and creating a lookup table. And so this would allow us to run a script that would generate a world for us, and then we could do some tweaks around the edges to place artifacts and make sure everything is correct. So that simplified the process and allowed us to make some more interesting worlds. A graphical tool was built, not by us. This was by a third party. And I can show you that now. Close some of these other tabs. So this was a Unity-based world builder. This came out more or less towards the end of the competition, but it's pretty interesting. If you want to quickly create a SubT environment, you choose your domain. I'll choose urban. And you start off with your staging area, and you can click the connection points and then just start adding new tiles, and it automatically places them appropriately. Oh, I did something wrong. It's highlighted red. I shouldn't do that. Let's try something different. That's better. And when you're happy with what you've built, you can also add artifacts. The one downside to this is artifacts only can be placed at connection points. It's not that big of a deal. You just have to go, if you want them in different locations, you'd have to go back into the SDF and move them around as needed. And when you're done with your world, you can download it. World. Every time you get an SDF file, and you get an SDF file, you can just load that into simulation. So that's kind of cool. Let's see. The one that I used a lot was just manual creation as well, using the Gazebo GUI. This was needed for some of the more complex worlds that I particularly had difficulty with loop closures and aligning tiles with different domain types. So I can just pop up one of these really quick to give you an idea of what it looks like. This was one of the final prize round worlds that mashed up all three different domain types. And let's see. This is loading all the assets from fuel slowly. So you can see some interesting aspects to this. You have your final staging area going into some urban domains. The urban domains transition into tunnel domains with different levels going on. And they transition again into cave domains. And you can get a sense of the scope and elevation changes. Some other interesting aspects. Since it was really hard to do some loop closures, we ended up creating these universal tiles, which I'm showing here. These are meant to be just kind of generic gap fillers so that you could actually get worlds to align without killing yourself. So we used these around in different places to make it possible to have some pretty interesting loop closures, places that overlap each other, basically trying to make it challenging for teams with their SLAM approaches. Okay, jumping back. In terms of releasing all these environments, basically for each domain, we would create a set of tiles and then release roughly 3 simple environments and 3 complex, more realistic practice worlds. The simple environments were designed to facilitate rapid testing, so you didn't have to load a really large world for developing or testing your solution. And the complex practice worlds were meant to be more indicative of what you would see at the circuit events themselves. In terms of the circuit events, we would create 8 private worlds. Typically, one of the practice worlds would be used for one of the worlds in the competition. We would just change the artifact locations around, and then we would create 7 new configurations. There's a few caveats for the final event. We used a few worlds that teams had never seen before. So these were kind of surprise worlds. One was the urban systems track. So this was a SAT-SOP course modeled after a never fully commissioned nuclear reactor just outside of Seattle. And World 4 was a combination, I believe it was a combination of cave tiles that teams hadn't seen, and World 8 was the systems track course. And of course, teams had not seen that before either. After each circuit event, the worlds would be released along with all the team's logs so that you had access to those worlds. Artifacts. We had artifacts designed specifically for each of the domains, and there were a few universal artifacts. So for each circuit event, it would be a combination of the universal artifacts and then artifacts from your particular domain. For the final event, there was this one extra special cube artifact that was thrown in there, and then you would see essentially all the artifacts in the final event worlds. Let's see some caveats in here. The gas artifact here is invisible, so I just wrote the word gas. The way this worked was it would be placed at the entrance to a room, and gas would be triggered by the presence of a robot, and a special gas sensor on the robot would be able to detect whether there was gas in a room or not. And the survivor, Rescue Randy model up here also had a thermal signature that was compatible with the thermal camera sensor in simulation. And the cave helmet had a light on it. And I think those were the only interesting aspects to the artifacts. All right, dynamic obstacles were added in the cave environment and also appeared in cave domain and also appeared in the final event. I can play this video while I'm talking. There were a couple of different types of dynamic obstacles. What you just saw there was a tunnel collapse, so that would block the entire tunnel. Those were called topological changes. Essentially, it was either going to be a large rockfall, which typically happened in a cave environment, or a tunnel collapse, which could happen in any type of environment. And the purpose here was to make it a little bit more challenging for teams to figure out how to navigate environments, especially when that environment suddenly changes. Then there was local obstacles that were small rock falls or a particle emitter that would emit dust or smoke. And these were just meant to be obstacles that a robot had to overcome, whether avoiding being hit or avoiding rocks that lay on the ground or getting through smoke. Each obstacle was triggered by the act of entering a region or the act of leaving a region, and that really depended on what we were going for. So in the video, you saw a quadcopter that triggered a dynamic collapse after it left. We didn't want to trap a robot inside the dynamic collapse, so it would be triggered after a robot left. Whereas some of these, the particle emitter or small rockfall would be triggered when the robot entered a region. Okay, let's move on to plugins. We developed a number of plugins for SubT. Most of them ended up in Gazebo itself, which is something that we try to do to the greatest extent possible. And there were a few that were very specific to SubT, mostly the communication model and scoring plugin. I'll talk more about the communication model. The scoring was handled by a typical Gazebo system plugin where it would know the ground truth location of each artifact, as well as the localization point for each artifact. The localization point is a particular spot on each object that is meant to be the ideal location that a team should report an artifact's location. So you would get a point if you could correctly identify the artifact and also identify its position relative to the command post within 5 meters of that localization point. And then a number of plugins were released in Gazebo. You can see the whole list there. I'll go over some of these in a future slide. These were released in, most of them were released in Dome, are now available in Fortress and beyond. All right, let's jump into the communication model, which was something, a bit of a challenge to implement, and also one of the major considerations teams had to take into account when developing their solution. So the whole point here was to simulate radio propagation in subterranean environments. So we had to do some compromises here because we couldn't do a really fine, high fidelity type of communication model because of the performance impact such a model would entail. So we developed an approximation, which ended up being a probabilistic model that took into account 2 different factors, one being range and the other being visibility. So both of these would be combined into a Gaussian distribution, and then you would, so every time a packet was sent, you would have a probability of success based on that distribution. The range cost function was basically just the Euclidean distance between source and destination. And the visibility cost function was meant to capture the act of trying to send data through complex underground environments, trying to capture the notion of sending radio waves through walls or around corners, that type of thing. We added in breadcrumbs, which were meant to act as radio repeaters. So these breadcrumbs could be dropped at any location within the world. And every time they were dropped, it would update the communication model. So this would affect both how the range and visibility cost functions would be used. And I will go into a quick demonstration just so it solidifies in everyone's mind. This is a very simple example of what actually went on under the hood. And I'm only doing visibility cost. You could swap out visibility cost for range with roughly the same results. So let's pretend each of these cubes here is a tile. They're connected to each other via those edges. So this would essentially be kind of a topological representation of a world. Each of the costs on the edge represents the visibility cost from traversing from one tile to the next. The higher the cost is meant to indicate the more complex or the harder it is to send data between those 2 tiles. So you can imagine a cost of 3 might be you have a very long or curvy tunnel segment, which is difficult to propagate radio waves down, whereas a cost of 1 might be a very short straight section, which is relatively easy to send radio waves down. So in this scenario, you have a source and destination, where the source is robot that wants to send a packet of information to the destination. We also have a maximum visibility cost. So anytime the sum of the costs over a path exceeds 5, then there's going to be no probability of communication. If it's 5 or less, then you are allowed to draw from that distribution in terms, and then determine whether you are actually able to, you'd be able to draw from the distribution to determine whether a packet is successfully sent or not. So in this situation, your cost is 5. You're just adding up 1 plus 3 plus 1, 5. So you are able to communicate, which is great. Source and destination can communicate. Now, if your destination robot moves to a new tile, you've added another cost here of 2. Now your visibility cost is 7, greater than 5. Math is awesome. So you can't do communication between these 2. All right, so let's now assume someone has dropped a breadcrumb, basically a radio repeater at this tile. Now suddenly you can communicate because your greatest segment cost is 5. This cost of 3 and this cost of 2. So breadcrumbs kind of act as an intermediary where we look at the maximum cost of a segment between the source and the destination, taking into account breadcrumbs, and use that as the visibility cost. And this would also apply for range. So that's what teams would see when they traverse the world and try to communicate with each other. They had to go through our communication model in order to send information back and forth. All right, moving on to the robots themselves. There were a couple different types of platforms that teams had access to. There were wheeled robots. Oh, I forgot one. There's wheeled, tracked. There was also legged robots and multicopters. Each robot had a sensor suite, which could be a combination of the sensors I listed here. Almost every robot had an IMU. I should say every robot did have an IMU, gas detector, and then some combination of air pressure, magnetometer, cameras, and LiDARs. There's no GPS allowed in the subterranean environments. Each robot also had a battery model. This was a linear battery model, which is available in Gazebo. It essentially has a starting capacity, and it will start draining once the robot moves. And once the battery is depleted, the robot is no longer able to move, but it can still compute. So you could still communicate between other robots with your immobile robot if you so choose. Breadcrumbs were optional. Some robots had breadcrumbs, others did not. And there was also marsupial capability. This was essentially a combination of a wheeled or tracked vehicle with a quadcopter or multicopter mounted on top. That combination could enter a subterranean environment, and at the team's choosing, deploy the quadcopter to fly around the environment. All right, moving on. So a team would consist of multiple robots, and each robot had a particular amount of credits associated with it, which was a reflection of the robot's capabilities. So this was meant to kind of force teams to choose carefully which robots were part of their team, and also limit the size of the teams so that we wouldn't be launching hundreds of AWS instances just to simulate one simulation run. So things that were taken into consideration were the type, the mobility type, the sensor suite, battery life, and whether they had breadcrumbs, and that would dictate the number of credits associated with a robot. And your team had to equal less than 1,000 credits. This number and the cost of each robot kind of fluctuated a little bit over the course of the program. I'm mostly reflecting what was in place at the final event. There was also a criteria that you could only use up to 5 of the same type of robots at any one time in your team. So you had to, if you wanted to use more than 5 robots, you had to choose a few different types. There was also a zero-cost space station. This would be spawned into the staging area. It couldn't move, but you could attach a Docker image to it and essentially act as a compute node. You could only have one of these. Let's see, there was, at the end of the day, the most popular robot was this one that you see right here, the CTU Crass Norlab X500. This was a quadcopter. It was the most popular because it was a good combination of cost to sensor suite, and it turned out that multicopters were very efficient at exploring the environments in simulation, mostly because flying a quadcopter in simulation is a little bit easier than flying it in the real life environments, because you didn't have to deal with dust or some of the more complex effects of quadcopters in narrow environments, such as backsplash and weird properties of how air flows over propellers. So that turned out to be quite useful for teams. Some of the least popular options were legged robots and the marsupial configurations. They just weren't the best combination of sensors and costs, and controlling them tended to be a little bit more complex. All right, so we bootstrapped SubT with a few robots that were labeled X1 through X4. So these were the X series robots that we first released at the start of the program. There were a large and small wheeled vehicle and a large and small quadcopter. Everything after that was contributed by teams, and they went through a pretty lengthy and rigorous review process. There's a tutorial on the SubT wiki that describes exactly all the steps that you have to go through. This kind of flow chart gives you an idea of the steps each team would go through. At the end of the day, a team would have a little document that would describe the robot, its capabilities, sensor suite, batteries, breadcrumbs, etc. They would submit a pull request to the repository. We would review it and validate it, run it through the world, make sure everything looked kosher, and it would, if accepted, get released into the SubT tech repo and make it. It would be made available to all the teams, and then every team would have access to one of these robots. All right, let's talk about the competition. I'm running low on time. I have to speed this up. Okay, from the competitor's perspective, you would register at subtchallenge.world. That would give you access to CloudSim, so you could practice. Otherwise, you could, clone our repositories and do all your local testing. Prior to each circuit event, there was a qualification round. This was meant to be a low pass barrier, so that excuse me. So we'd have a set of teams that were actually actively participating in developing solutions. Then there would be the circuit event itself. You would have a time window in which to submit your solution. You could submit multiple times. We would just take the last submission, use that, run your solution, get some results, which mostly were log files and scores. And after publication of the results, you would get your logs, and you can review logs and submit any complaints that you had about scoring or anything of that nature. Turned out, so we're very familiar with using AWS, and it worked out really well for this competition. It gave us the ability to have some pretty fine-grained control over security in terms of making sure that team solutions were kept private and one team couldn't access another team's solution. And similarly with log files, it was relatively easy to get that all up and running, and played nicely with CloudSim as well. So I highly recommend them. I should also say I haven't tried the competitors, so it could also work really well on Google Cloud or Azure. So from our side, when we were actually running a circuit event, we would copy the ECR images that teams submitted to a new secret private repo so that a team couldn't submit a new solution after the deadline. And then we would run those solutions all simultaneously, as simultaneously as we could on AWS. So what that looked like under the hood was us submitting to AWS an on-demand capacity reservation in ODCR. They would essentially give us hundreds of machines, all reserved for our use, and CloudSim would go off and deploy simulation along with the provided solutions on those machines, and keep track of all those running instances, record the log files, and keep adding and requesting new machines until all the runs were complete. On the finals, the heaviest usage we got to was running 200 simultaneous simulations, which ended up using around 1,000 GPU machines all at once, which was pretty cool to see. Also really expensive. I'm glad I wasn't paying for it. Let's see, there were definitely reruns that took place. And these reruns were based on whether CloudSim experienced an error or Gazebo experienced an error, or after some log inspection, we decided that we needed to rerun a solution. And I'll get into some of those errors in a bit. Along the way, we found that AWS US East has the most G3 instances. So if you're ever using G3 and you want thousands of those, go to US East. And the paid AWS support is really excellent. If you ever want to experience some top-notch support, just pay them a lot of money, and they will really take good care of you. Okay. After each circuit event, there was a post-processing step that took place. We would generate a report that contained all the teams, all the runs, and information about score, duration, distance metrics, artifact reports, and whatnot. We'd use this to come up with the final rankings for each circuit. We also ran a log file checker. So this was meant to catch any problems, errors, or instances of cheating, of which we found no attempts to cheating. But we would look at ROS logs and event logs and the Gazebo logs as well to check for lost messages, sequential sensor messages, other events like proper start and stop of simulation. And then we generate videos. So this ended up being a series of scripts that would capture interesting events during the run of, during each simulation run. One of which you see here. So typically we'd have a camera that would attach itself to a robot and follow itself through the environment. We capture things like anytime a dynamic obstacle was triggered, or the robot approached an artifact, or traversed stairs, or things of that nature. Along the way, we initially did all this video generation somewhat manually. The pandemic actually helped in this case because I was able to go into our office and just commandeer a lot of the currently unused machines and just use those for video generation. Fortunately, I did get that moved into scripts and deployed on the cloud, which was much more convenient than running around the office. Okay, let's talk about CloudSim a little bit. The whole goal of CloudSim was to have a level playing field for all competitors and offer 24/7 practice. This was all based off of Kubernetes. We've had a history of developing CloudSim for different competitions. This is kind of the latest and greatest iteration of CloudSim, and one that we're pretty much going to stick with going forward until we get crazy and decide to rewrite it. It's basically a library of tools that allow you to build up an application. And that application typically consists of a set of states in a state machine that dictate how and what to do using various cloud resources. So that could be, I want to launch particular EC2 instances with particular Docker images and with these network configurations in order to run a competition or to host a robotics course, or maybe even run CI, for example. So it's meant to be really configurable and tailored so that you can kind of abstract away cloud capabilities and just kind of think about it in terms of what you want those cloud resources to do. For the SubT case, this is what it looked like. There was an EC2 instance running simulation. There was one EC2 instance per robot that contained the bridge container that spanned ignition to ROS, did ROS logging on this side, and also offered a way for teams to ROS bag their own custom topics. And then there was also a special mapping server in a separate EC2 instance that allowed teams to submit log mapping information. And coordination between simulation and CloudSim took place via WebSocket connection. A separate WebSocket connection was also used for visualization purposes, which I'll segue into right now. This is basically building off of GZ Web, which existed as a tool in Gazebo Classic, and we've now transitioned it over to support the latest iteration of Gazebo. This is all based on Gazebo transport sending protobuf messages over a WebSocket server. So the nice thing here is that we don't have to do any deserialization and reserialization or changing the types of messages that come from Gazebo to the browser. It's just a straight pass-through, which is a nice feature of protobuf. There's libraries in JavaScript and a lot of different languages to handle parsing of those messages, and allows us to visualize local running simulations or remote running simulations. We ran into a number of errors on CloudSim, and the errors decreased over time as we got more and more competent at managing our cloud infrastructure and improving Gazebo. I don't have time to go into all of these, but I know this is being recorded, so if you ever want to kind of look at what we ran into, feel free to peruse this slide. It basically ran in, split down between seg faults and problems in simulation due to physics or collision detection. And on the cloud, it was mostly us learning how to properly handle errors returned by AWS and errors returned by Kubernetes. New Gazebo features, really quick. We added the concept of levels, which allows us to simulate, oh, that is annoying. Simulate different segment, only a subset of a world at a particular time based on the location of where robots are in that world. We updated our logging infrastructure to use SQLite3, added PBR rendering, the linear battery model I talked about. There's a Collada world exporter. So if you have a world and you want to say, render it in Blender or another tool, you can export the SDF to Collada. Thermal cameras, you can see it down in this picture right here. That's the Rescue Randy with a thermal texture map applied. Particle emitters you can see right now in the other window. The performer detector and trigger and detachable joints is a really flexible framework that allows you to have pretty dynamic environments based on the presence of robots and how they move through the environment. So you can, I think the last thing I did here was have a minecart on a slope with a detachable joint being triggered by a robot moving through the environment. So you can almost have like an Indiana Jones type of environment based on where a robot is in the world. All right, I'm getting towards the end. So this is, let's see, a plot of each team in the virtual competition, the points that they receive in the final competition compared against the number of practice runs that they did on CloudSim. I was kind of hoping to see some correlation here. Turned out I couldn't really see one. Maybe if I stand really far back and squint my eyes, I could see something, but I didn't really see any strong correlation between the number of practice runs teams did on CloudSim with their final scores. Here are the overall scores for the 8 worlds in the final competition. I mentioned that there was a few worlds, 4, 5, 6, and 8, which were unseen to teams, and the other worlds they had a lot of time practicing in those. So you can see a clear dip in the scores for those worlds.
Nate, do you have much left? Because we're on.
That's it. I'm done. Okay. I can take questions. I know we're out of time. Sorry I went long.
Okay, thank you for the presentation, Nate. Maybe we can do a couple questions. We started a few minutes late, so I think we have time. Anyone has a question for Nate? Or maybe not. Maybe I shouldn't have cut you short.
I should have stopped earlier. Some interesting things. We did generate 2.5 terabytes of data, so that's cool. I had to get a whole special hard drive just to be able to process video logs. Let that be a warning for you if you ever do another competition.
Okay, I think if nobody has questions, we can wrap it up here. We are. It's been an hour of meeting, so I think yeah, let's wrap it up. Thank you again, Nate, for the presentation. This video will be uploaded to YouTube to the playlist together with the rest of the community meetings. And next month we're gonna have another meeting at the last Wednesday of the month, like we always do. Thank you everyone for joining. Bye bye.